This is Honors Pre-Calculus, section 4.1, page 1. Today we're going to start off looking at a polynomial function and write that definition. A polynomial function is a function in the form f of x equals a sub n times x to the n minus, a sub n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus etc. all the way on down to a sub 2 x squared plus a sub 1 x to the first plus a sub 0. I know this looks confusing, but just hang on and we'll kind of explain what everything is here. N is a whole number. So we have some whole number here, then look at the powers. The next power down is one less than that. So maybe this n was a 7. Then this was x to the 7th. Then this term would have been x to the 6th. Plus this term would have been x to the n minus 2 fifth. Plus, and it keeps going all the way down until we have an x squared term, and then an x to the first, and then x to the 0. The a's in here just number the coefficients. So a sub n is the coefficient of the x to the nth term. A sub n minus 1 is the coefficient for the x to the n minus 1 term, etc. You might recognize this a little bit better if I wrote an example for this. F of x is 4x to the 5th plus 3x cubed minus 9x squared plus x plus 13. That's a polynomial function. Things that can't be in polynomial functions, sometimes it's helpful to think of what can't be there. There are no radicals. So no square roots, no cube roots, no radicals at all. No fractional exponents. On the variables. No negative exponents. On the variables. And no variables in the denominator of a fraction. Some other related vocabulary that we need to talk about. You've heard most of these words before, but let's just kind of run through them and iron them out and make sure we have them. A term is the product of a constant and a variable. Coefficients, that's the number being multiplied times a variable. A leading coefficient. The leading coefficient is the coefficient of the term with the highest degree. And what is a degree, you say? The degree of each term is the sum of the exponents of the variables in the term. The degree of a polynomial is the same as the degree of the term with the highest degree. So if we look back up to the beginning, this example that we had, the degree of this term, that's a degree 5. This term is degree 3. This term, degree 2, degree 1, degree 0, or a constant term. The degree of the entire polynomial is a degree 5. The cubic term up here is 3x cubed. The quadratic term, negative 9x squared. The linear term, linear is degree 1, so that linear term is just x, and the constant up there, 13. All right, when we look down here and look at these, are these expressions polynomials? If not, why not? All right, looking at this one, 3x squared minus 5x. Looking back at our list of things that can't be there. There are no square roots, there are no fractional exponents, there are no negative exponents on variables, and there are no variables in the denominator. This is a polynomial. Yes. This one, no, because there is a variable in the denominator. Okay, but what if I had something like this? X squared plus 3 all over 7. Is that a polynomial? Yes, it is. That is a polynomial because it's okay to have a number in the denominator, but not okay to have a fraction in the denominator. Let's turn the page and go to page 2. Remember, if I'm going too fast here, feel free to pause it and stop, rewind, pause, catch up, etc. Okay, this next one here, we're going to take a look at graphing some functions here. If we have a linear function, we know that we get a line. And that line can either have a positive slope, a negative slope, or 0 slope. A line that has no slope is vertical and it is not a function, so we are not taking a look at that. Quadratics, we just spent a whole chapter graphing lines in quadratics. A quadratic is a parabola. And we remember from last chapter that a parabola can either open upwards or a parabola can open downwards. A cubic function has a couple of different shapes that we could have. A cubic can look something like this. It can be the reverse direction and look something like that. Or a cubic can do this. Or again, reverse, something like that. Those are all shapes of cubics. They don't have a special name, they're just called the graph of a cubic function. A quartic, degree 4. Degree 4 can look like, almost like a parabola. Looks like this, or upside down, or a degree 4 could be something like that, or it could be upside down, and it could be upside down where kind of the heights of these two humps, if you will, could be exactly the same. So those can be kind of on the same level, or they could be on different levels. All right, now putting all of this information together, if we have an odd degree function, so linear is odd, cubic odd, and what I want you to notice out of these, the odd degree functions, is that one end goes up, one end goes down. One end up, one end down. Likewise on the cubics, one's going up, the other one down. Okay. If we have a positive leading coefficient, the left side's going down and the right side's going up. And if we're the other way with a negative leading coefficient, then the left side's going up and the right side's going down. For an even degree polynomial, that's quadratic, quartic, I better write down that these are even degree, not just odd and even. You might think that those are odd and even functions, and they are not necessarily odd or even. It depends on the graph itself. It's just an odd degree. Odd degree. Okay, even degrees. Both ends go up or both ends go down. Both ends up is a positive leading coefficient. And both ends down is a negative leading coefficient. Both ends up, you're going to have something like this. It may bounce around in here, or it may just connect. Likewise, both ends down, both sides are going down there. Looking for a calculator here. I am going to have to trust that you will take a look at these on a calculator. I do not have a calculator with me right now, but if you go ahead and compare the graphs of y equals x squared, y equals x to the fourth, and y equals x to the sixth, put this one in as y1, y2, y3, and let's look at them on a pretty small viewing window, in that let's let your x's be between, say, -2 and 2, and the y's also between -2 and 2. And when you look at these three graphs, you should see, pause the graph, pause this right now and graph them. I mean it. Pause this right now and graph all three functions on your calculator. Seriously. Welcome back. I know that you followed my directions and graphed these on your calculator. And when you did that, you saw that all three graphs have 3 points in common. Those 3 points in common were -1, 1, 0, 0, and 1, 1. And you also see that the higher degree polynomials are more squarish on the bottom. More squarish, if that's a word. Much more squarish. So an x to the 6th is going to be more like that. And an x squared, very curvy. And those will intersect at that point. 1, 1, and 1, negative 1. Okay? All right, same idea now. Compare these three graphs, y equals x cubed, y equals x to the 5th, and y equals x to the 7th. Again, please pause the video and go ahead and change your graph. Same window that we had before. Pause your graph, not pause the graph, pause this video, go ahead, graph them up in your calculator. Welcome back. And I know that you saw when you graphed these three that there are 3 points in common. They are -1, -1, 0, 0, and 1, 1. And again, just like with the even degree, the higher degree graphs are more squarish. So while a cubic, just y equals x cubed, is going to look something like that. Y equals x to the 5th or x to the 7th is much more squarish, if you will. So this one would be more, this orange one, more like an x to the 5th or an x to the 7th, and this purple one like an x cubed. All right, moving on. Let's look at this page then. We are going to sketch a few graphs without your calculator now. So I want you to sketch y equals x minus 2 to the 4th and y equals x minus 2 squared. You should be very familiar with that second one. Y equals x minus 2 squared. It's a parabola opening upwards, and the vertex is at 2, 0 because we have shifted 2 units to the right. So we're going to hit right here. We also know that 1 unit to the right and left, we're going to get 1. And 2 units, we would hit a 4. That's y equals x minus 2 quantity squared. Now let's go ahead and put in y equals x minus 2 to the 4th. We know it hits these same 3 points in this beginning, kind of that vertex, and then over 1 unit. So we're going to hit those. If you want to check another point and plug this one in just to see how steep it is, if we plug in a 0 into this one, we're going to get a negative 2 to the 4th, which is a positive 16. So I have to turn the page so I can draw this. This is much more square here. And it's going to come up. And it hits way up here at 0, 16. Much steeper in here. And we're going to hit another point way up here at 1, 2, 3, 4, 16. So much squarer down here on the bottom and much steeper, much faster inside. Okay. Look at this last one for today. Sketch y equals negative 2x to the 5th plus a 3. And, oh, we know we are going to reflect over the x-axis. We have a vertical stretch by a factor of 2. And we're going to shift up 3. Sketching this graph up 3, so we're going to hit right here. And then normally on an x to the 5th graph, when we go 1 to the right, we would have gone up 1. But this time when we go 1 to the right, we're going down twice as far. So right there at 1, 1. And if you're not sure if that point is right, plug in x is 1 into here. When you plug in x is 1, you will get negative 2 times 1 plus a 3, which is 1. When we plug a 2 in here, let's just check that one. Negative 2 times 2 to the 5th. 2 to the 5th is 32 times negative 2. Negative 64 plus 3, negative 61. Holy chimney. Oops, this one here. Forgot to do my stretch. And it's very steep, but very squarish in the beginning, and then very steep after that. All right. Perfect. Thank you so much for tuning in. And this one is day 2 down here, so we will pick that up when I return to school. Have a good day. Bye now.